welcome to another problem session. So this problem is we are doing this nowadays, this problem from JEE Advanced Phys 2025, and this is paper 1, and this question 13 from there. Actually, this is quite a good question from you might say it's from atomic physics. Okay, so let's read this question. So we have a electron in n equals 3 orbit of a hydrogen-like atom with terminal Z. So basically we have Z protons over here and some neutrons. Let's see, n neutrons, and we have Z electrons going around it. So ZE electrons around it, and you look at one of the electrons. So here is an electron. So that will be an atom. Okay, that will be, the whole thing will be a neutral atom, right? Neutral atom. But what you do is you strip off everybody except one electron. So that's a hydrogen-like atom. So you have a Z proton and some N neutron, and so one electron, just one electron going around it. So if you set up the equation for this electron, it will be like a same as in terms of how it will look. It will look like what you have, one proton and one electron. This is the hydrogen atom. So this is hydrogen like atom. So it's like one electron system with a whole bunch of different number of protons. And so this is a so like if you took like a helium and it stripped one electron from here, so this will be like this, an example with the Z equals to 2 and N equals to 2. I mean, helium is like a 2 protons and 2 neutrons. Okay, so that's so we are in this kind of situation, and we are in, this is n equals to 3 orbit. So we're talking about this electron. So looking at that electron, and it says look at absolute temperature T, a neutron having thermal energy this has the same de Broglie wavelength as that of, so you have to know what de Broglie wavelength has to do with temperature or energy of the electron. So the other thing to understand this question is to understand what's a de Broglie. It's a French name, so a whole bunch of things written down without pronouncing them. It's not de Broglie, it's not that. Okay, so this de Broglie wavelength is so what you have is if the electron has a momentum p, so momentum p, so anything that has a momentum p has a, you can think of that a matter wave of h over lambda. So that will have wavelength lambda, and h is the Planck constant. He also showed that if you do this, then you actually can show that this electron or any system, this electron will fit, because n equals to 3, then it will fit one wave, two wavelength, three wavelength. So it will fit three wavelength in here for n equals to 3. So in here, if you want to say what's the wavelength associated with that electron, you could say if that distance is Rn, so I go 2 pi Rn and I go n times lambda associated with this orbit electron. So like that will be, you can show that this will be the case by using this and this, you can show that. So this is also, all of this is associated with Bohr's quantization condition. So which we know that Bohr said it's just ad hoc. This is ad hoc. He claimed this is a case to derive relations which were experimentally reasonable. So angular momentum L, which will be something going in a circle like that, will be mvr. So this will be continuous in general, right? Speed and half-hour electron can be continuous. He said this must be equal to nh over 2 pi. I mean, this one must be what we write nh bar nowadays. nh over 2 pi. So it's n has to be just integer multiples of this. So this stuff is all and that stuff, they're all connected. Maybe you've seen the derivation. Let's just make sure that you are a little bit familiar with all of this. So this will be the mv, will be p. So you have a p times r. Suppose I'm in the nth orbit. So that will be n, and it will be n. So this nh over 2 pi. P, I'm in the nth orbit, so let's call that Pn, all of an nth. And so let's call it, rewrite like 2 pi, bring 2 pi on this side. So you have a 2 pi Rn is nh over p in that orbit. And so it says Pn is going to be h over lambda n. So this n h over lambda n, I mean it's h over lambda in the orbit. So this will be n lambda n, and that will be that. So Bohr's quantization is actually leads to this momentum being related to associated wave. So this is like a particle property, and this is a wave property. So this is like a revolutionary thinking that a particle could be thought as some kind of matter wave, and you could associate a wavelength with it, and then you get a quantization condition, Bohr's quantization condition. So this question is saying, trying to see if you understand all of this, okay? These ideas. Not just memorize the formula, just understand the ideas, okay? So let me expand this a little bit so I can read. Eyes are a little bit getting worse now, so I see a big one to see it. All right. So we have, the question is that we have a de Broglie wavelength of a neutron, which is same as the wavelength of this electron. So you have two systems. So in here it says wavelength of the, in this condition it's saying that, okay, read this to let me kind of move this, okay, with all of this all of those writing. I just disappeared for me. Okay, so move out of this. So now we have background already done. Let's do it out. All right, so it's saying that this electron of lambda of the electron in the nth orbit, n equals to 3 of the electron, equals to lambda of the neutron, okay, with energy equals to energy or kinetic energy equal to kb times temperature. So this is the condition given. That's how I read this condition. If you say, if you implement this, then then you'll find the temperature is this big giant formula, this big numerator, and then there's alpha, and then this denominator. And so question is, what is this alpha? Find alpha, numerical value of this. It's a numerical value. Okay, so with this condition, so if I'm n equals 3, what is going to be lambda? And we already said 2 pi rn, 3 lambda n equals to 3, right? 3 lambda 3 for the electron will equal to 2 pi rn of the electron. And so 2 pi rn is going to be n equals to 3. And another formula you might remember, Rn of hydrogen-like atoms, Rn is n square A0 over Z. A0 is the radius of the first Bohr orbit of hydrogen atom, okay, and which it says over here. So this is going to be like that. So we just 2 pi n square is 9 A0 over Z. So this is 18 pi A0 over Z. And then you put lambda n equals equals to 3 for electron. You don't have to decorate this in the test time. I'm just writing it for ours, just for here, okay, because I'm doing it out and doing it out slowly so I understand, and I'll probably do it much faster when I'm in the test. So how do you do this guy? Well, I have kinetic energy equals to kBt of this neutron, and kinetic energy is going to be half mv n neutron square equals kBt. Okay, this you can write down, divide by m of the neutron, then square. This becomes p square. So then this becomes p square equals 2n kBt. So p square becomes from the de Broglie, p square will be h square over lambda square. So we want a lambda n square will become what? Lambda n square will become from here h square over 2mn kBt. Because we want t, we don't want a square root in there, so let's, because we're going to solve for t, so let's just say what the t will be. So t will be, I'm not going to solve it here, but this is the answer right now for lambda n square. And this side is this answer, so square this guy also. So lambda electron square equals to 36 pi square a0 square over z. So now, because of this given condition, I can equate this with that and solve, right? So let's equate this, or we can equate 1 over lambda e square equals to 1 over lambda n square, the inverse of that. So this was 2 mn kVt over h square equal to, I think I forgot the square here, but z square over 36 pi square a0 square. And now we can just write t. So we can try to write t equal to z square h square over 72, we have a factor of pi square a0 square, mn comes down, kb comes down. So it's the numerator of that, and the rest of the factor, the denominator is that. So this is the alpha. So alpha is 72. Yeah, so actually this is, you can see, I know there are a lot of algebra here, but the main thinking was done over here. Do I know what hydrogen-like atom means? Do I know how to think of de Broglie this way? This is a de Broglie thinking, like packing waves in each of the orbit. So this is basically, this is, you go all the way around one circumference in the nth orbit, you're going to pack n times the wave length. Okay. And another, this is also de Broglie thinking for every particle. Momentum and wavelength are inversely proportional to each other. They're not inverse to each other, yeah, inverse of each other, and it's a Planck constant. Their product, p times lambda, is h. You know. All right. Sometimes this is written p is written p. You have h over lambda, but you say I'm going to do h over 2 pi and 2 pi over lambda and h over 2 pi, and you say this guy is h bar and this guy is k, h bar k, wave number. And this is the physics people's wave number, not chemistry. Chemistry wave number is, that's why sometimes in the introductory books, physics books, we don't write this much. K in chem is 1 over lambda, but in phys, K in physics will be 2 pi over lambda, and that has to do with we want to keep the 2 pi's out, and we want to use h bar because h over 2 pi appears a lot of formulas, and so like over here, h over 2 pi comes in here, same formula. So h over 2 pi comes in many places, and you want to create a symbol for that. Okay, that's it for this problem. So I'll stop now and we'll see you in another problem. Bye.